very much, Frank. So, is the presentation visible? Is it all right? Or
yeah, yes.
Okay, good. Because I actually don't use particularly Zoom that often. Okay, good morning, afternoon, or any time of day that you are currently going through. My name is Karel Zidek, and I work at the Czech Academy of Sciences at Research Center Topec, which is actually part of Institute of Plasma Physics, IPP. On the other hand, we are mostly working on optics, really. So we are Applied Research Center collaborating a lot with industry, producing special optics, working on space projects, prototyping for laser industry. We do quite some research in glass processing, thin film deposition, and important part is also material research and spectroscopy. And this is where my group of computational spectroscopy and imaging comes in. So here you can see the members and the latest group photo from our last meeting, which, as you can see, was affected by COVID as anywhere else on the earth. And together, we address quite a broad range of topics. So we focus on compressive hyperspectral imaging. We did some, I think, nice work in imaging in ultra-fast spectroscopy. We look for new ways, new approaches to address fluorescence lifetime imaging, so that you can check here. And our interest now turns more to ultra-fast spectroscopy and using compressed sensing in measuring ultra-fast processes and nonlinear processes. So our work is kind of connected together by the randomness. So when you try to use compressive imaging or compressed sensing, and I cannot go here much into details, you need to use random patterns to measure, to do something. And if we try to measure fast processes, we need random ultra-fast pulses, random pulses on the femtosecond time scale. And also we need to know how these pulses look like. So when you want to measure something, I mean, if you want to measure something which is really fast, a typical approach would be that you take something which is much faster than this. So here you can see a photo of Lex Augustin from Australia, who captured a bullet, flying bullet with a regular camera. But you can tell that he could use a regular camera, but what he needed was a very short flash of light. Microsecond photographic flash, which he used with a good timing, and he could capture this very fast process. All right, but we want to basically do the same. We want to capture something very fast, our femtosecond pulses. But how do you want to measure femtosecond pulses if these are the fastest things that you can actually get? And the answer would be, okay, you need to use the very same thing, the same pulses. So this is an approach which is well known for several decades. In ultra-fast spectroscopy, this is called autocorrelation measurement, where you take two replicas of the same pulse. So you see here pulse 1, pulse 2. You adjust delay between them, and you send them through a nonlinear crystal. For instance, BBO, generating some frequency, meaning that you generate from 2 photons of these 2 pulses, you generate one which has double frequency, and you detect its intensity. So if these pulses overlap a lot, like here, you see a very strong signal. If these pulses do not overlap in time, you see that the signal is very small, just subtle. There is an exact way how to calculate that. So if you have a simple pulse, you can tell approximately how long is your pulse. This works well for simple pulse shape like Gaussian shape, etc. But imagine that you want to know more, that you have some very complex pulse and you want to see how this pulse looks like. And then this method actually fails to work, because you can see that you can take very different pulse shapes, like here, and get almost the same autocorrelation. So you cannot really tell which is which. All right, but there is a way how to overcome this problem. And this was invented already in the 90s by a guy called Rick Trebino. And it's called frequency resolved optical gating. Or probably you've heard about it more like as its abbreviation, FROG. So this is now fairly standard way how to measure complex pulses. So you see it basically looks the same as the previous method. So you have, again, two replicas of the same pulse, and you adjust delay between them. Again, you create some frequency generation, or you induce some frequency generation. But now, instead of measuring the intensity, you measure spectrum. And that's quite a different case, because in this, if you measure the spectrum, you also have the information not only about intensity, but you have there also the information about the phase. So basically now if you scan the delay and you measure spectra, you get a trace like this. In each case, the spectra are slightly different in each delay between the two pulses. Okay. Good information is that each trace is unique for each pulse, or even this experiment is highly overdetermined, meaning that you basically have more information that you need for the pulse retrieval, and you can even do some self-check whether your reconstruction is okay or not. And well, the dark side is that you cannot just take this trace and calculate explicitly the pulse. This is not possible. So instead, you need to take some initial guess and use an iterative algorithm to reconstruct, to create a trace which resembles the original one. And then you can tell what is the actual pulse shape, like this in this case, and the phase in time or spectrum. So basically, this method allows you to reconstruct even a complex pulse shape. If you are interested how this looks in real, or let's say these are some old photos, now these setups are a little bit updated, but we use laser from light conversion pharos, which uses non-collinear optical parametric amplifier to tune laser pulses in this range. And then we use a thing which is called 4F pulse shaper. Again, we could spend long minutes explaining about this, but basically take it as a device where you can adjust the pulse shape or change it. And we have a setup which measures the actual pulse length, pulse shape. So basically, you can see that here to get the experiment right, there are several preconditions. So you need to be able to set timing between these two pulses, and this is done by this delay line here. But setting precise delay line, setting precise position of delay line takes time, right? Because if you send your delay line to a certain position, you want to measure with certain delay. So you tell the delay line, okay, move to this position, and the delay line moves there. And it takes actually quite a considerable time to settle down and to adjust to this exactly to the set position. So if you want to set it with a high accuracy, first of all, you might need to buy a more expensive delay line, meaning this device which is setting the delay. And you may need to wait a little bit longer for the delay line to settle down to this position, and then you can measure. So instead, we were thinking, okay, what is the actual lowest accuracy what we can use? Meaning that we set the delay line to a certain position, but the delay line might end up at slightly different point. Maybe we will care, maybe we will not care. That's the question. But if we relax this accuracy, we see that instead of getting some nice frog trace like here, we get a corrupted trace, which you can see here. And this is basically the only experimental information together with laser spectrum, which we use to reconstruct the pulse. So overall, the goal is to measure the pulse shape as fast as you can, because you want to make, for instance, many experiments with different pulses. But at the same time, you need to do it in the way that your pulse shape, that you can still reliably tell, okay, my pulse shape looks like this. And one of the connected issues is that it actually differs what you are interested in and what you can measure, right? Because the thing that you care about is how precisely you can reconstruct your pulse. So this is a result of some of our simulations here, where you can see the original pulse, the blue shape, and the reconstructed pulse from the frog trace. And the more your picture will look like this, the better for you. This is a little bit worse, but still acceptable result. And so you are interested in this kind of error, how much your reconstructed and simulated curve pulse shape look, or actual and the reconstructed pulse shape differ from each other. But this is not something that you can access in the experiment. Instead, you can measure this error, which is the one that you get, like the measured, sorry, this is simulated, this is measured frog trace. So this is the corrupted frog trace, the one that you measure. And this is the frog trace that you get from the reconstruction. That you can always get, because you will measure certain frog trace, you will reconstruct it, you will see the difference. So you can tell how much these two differ. And the natural question is, okay, we know this error, this we always know, but we never know this kind of error, which we are interested in. So is there a way how we can tell whether our frog measurement is good or not? And does it matter whether our delay line is good or not? Okay, so we took two cases in our simulations, and we first tried a case where the delay line is actually following very precisely the set position. So we assume that the difference is with a standard deviation of 100 nanometer. Good. And if we assume that, we see very clearly that we get a strong correlation between these two errors. Meaning, okay, if our measured frog trace does not agree with the reconstructed one, we have a good indication that something is wrong, that our reconstruction didn't work fine. Because sometimes, you know, you do iterative reconstruction. Sometimes it could happen that your initial guess is not good and you end up in a badly reconstructed pulse, even though you have good data. Or you have cases like this. So here you see strong correlation. If you know this error, you have information about this one as well, which is good news. And now we can go to the opposite case. So we have a case where the delay line tries to reach the position, but stays somewhere within 1 micron, or with standard deviation 1 micron, away from the ideal case. And we see that in this case, we get sometimes very good reconstruction, this intensity error. To remind, this is a measure how well you reconstruct the pulse shape. So sometimes you can reconstruct the pulse shape very well, sometimes not as good, very bad. But unfortunately, there is really no good way how to tell whether from the experiment, whether your experiment went right or not. So one of the, let's say, apparent thing would be, okay, maybe it matters how I do. Maybe some noise patterns are better or worse than the other, so maybe I can be lucky and get a better measurement. So we took 2 random pulses. They have certain number so that we can repeat the measurement. And we tried different simulations. These are simulations now. So we simulated frog traces with quite bad jitter, meaning that the delay line is not very precise. And we tried to measure 4 different times, or simulated several times, and see how well we are doing. And it turns out, not too surprisingly, that, okay, as before, you can see that you can get, again, for some measurements, much better than reconstruction than for the other. Like here, the red one gives much better result than this one. But on the other hand, from the experimental data, you cannot really tell which is the good one. So unfortunately, you need to go for a reasonable jitter value. It's not like you can just measure again and again and say, okay, later I will pick one measurement and see this one is good. So then the natural question is, okay, if we need to use a delay line with a reasonable delay line jitter, with a reasonable positioning error, what is the actual error? Well, how precisely my delay line needs to work? And here we did testing on several different pulses. So here you see some very short random pulses. Such pulse would look like if you had a titanium sapphire few cycle pulse oscillator, and you would carry out pulse shaping. Here is another case where you see a random pulse like this. It's the same set of pulses, but this time with a stretch in time, so smaller bandwidth. And this is the same type of pulses, the same bandwidth as here. Bandwidth means that if you your laser spectrum is brought spectrally broad, how broad it is, and the more broad your spectrum is, the faster pulse you can get. So these are equally broad spectra, but in this case we randomize the pulse much more, so we get a pulse which is more stretched in time. Okay, and basically it's interesting first to compare these two, because these are basically 2 pulses just stretched in time, and something which is not very let's say, surprising that if you stretch your pulse 4 times in time, you need 4 times lower precision of your delay line. This is kind of understandable because your frog trace also stretches in time. You don't need to reach such a big precision. So, for instance, here you can see that these cases 250 and 1000 jitter are comparable in these two pictures here. And note that this is now logarithmic scale. This is not linear. So this is the error of the pulse, how precisely you determine pulse, and this is the experimentally accessible frog error. And you can see that for the pulses here, we get very, very similar values. In general, we observe that we get better agreement if we have more complex pulses. So this is kind of surprising in the sense that if you have more wildly oscillating pulse, it is actually easier to measure this type of pulse. And one of the possible answers is that it stretches more in time, so you basically cover more time points here. And here we did some testing where we tried different sampling, different number of measurements to see that we don't get an effect when we do the simulations for different number of measured delay points, and etc. So this basically tells you that your error induced by the jitter does not change if you try to measure more data points. Doesn't really help. Okay. So here the answer was that we wanted to know what is the acceptable delay line jitter, and the one which we got based on, for instance, comparison of the noise of the reconstruction error that you get from the noise, because every measurement suffers from a certain noise level because of shot noise, because of certain noise sources. This jitter is basically one of the noise sources in your measurement. So if you want to get a result which is comparable with other noise levels, you need to have a delay line which adjusts the delay approximately with the same precision as your pulse length, or bandwidth limited pulse length. So if you have laser which gives 100 femtosecond long pulses, you can actually get pretty good result if your delay line is not very precise, and it can just adjust the delay with a comparable precision, which is quite surprising, because this means that the frog reconstruction is quite robust against these type of errors. Okay, but we wanted to speed up our measurement even more. So of course, the way that we measured so far was this. So we shifted our delay line, stopped it, and acquired one spectrum, did it again, stopped, acquired second spectrum, third, etc. And here until we measured the complete frog trace. And this takes some time. So instead, it makes much more sense if you want to speed up your measurement to use something which is called sweep mode. So in the sweep mode, your delay line, you continuously change the delay between the two pulses, like this. And instead of stopping the delay line, you do the measurement in between. And of course, as in the previous case, you get some error level, some jitter, because as in the previous case, the delay line cannot go with an ideally constant velocity. So the speed, it can be slightly faster here, then the controller will slow it down here, etc., etc. So you still have the jitter issue here, but beside that, you need to see whether there is this is a problem when you average your frog trace over long time, over a certain range of delays. And it turned out that it actually does not make very much difference. So when we did our simulations and we tried to speed up the measurement, decrease the number of measurements and everything, as you can see here, you get very very nice agreement between the simulated and the reconstructed pulse. So in fact, it seems that really sweep mode is not causing any trouble in this case. And and related to that, here you have a measurement of a laser pulse of 20 nanojoules, which was taken from our non-collinear optical amplifier. We can get nicer pulses than this, but I like that we can get some nice features here in the frog trace. And here you can see that we can measure very reliably the entire frog trace with acquisition time of 40 milliseconds. So basically, one experiment, one picture like this takes 40 milliseconds now. If you want to see how it looks altogether, this is a series of experiments which we did again for the pulse emitted from NOPA. It's as you can see, a very similar case. Just here are wavelengths and here are frequencies. So the picture is turned upside down. And these are different compressions of the same pulse. So you basically take the same pulse and you compress, or for those who don't know that much about ultrafast spectroscopy, you basically control the change phase of the pulse, and you can also reconstruct the frog trace. And we see that we can describe our pulse very well, meaning that for different realization of our experiment, different compression, we can measure very well the pulse shape, and all these results play together, which was really great news. And so these are phases that we got for different reconstructions. You can see that they differ quite a bit on the outskirts, but this is basically because there is almost no laser intensity in this part. So here it doesn't really matter what the phase shape looks like. Okay, so by this, let me summarize my talk. So we carried out a study of frog measurement where we try to reach as fast frog measurement as we could get, and we did not see any apparent limitation for the frequency use of optical gating when it comes to sweep acquisition. So this is kind of a measurement mode which we use, that we let the delay line continuously move, and we measure our frog traces in between. So based on that, we were able to measure one frog trace within 40 millisecond acquisition time. This is very important for us because we want to measure with a high number of random pulses. So we need to measure a big number of random pulse shapes. So we need to be able to tell the shape. We observed that the main limitation in our case was the delay line jitter. So basically, how precisely the delay line can control the position of the how to say it, of the ideal track and the signal level, meaning that in principle we could actually measure much faster than this, and we have a spectrometer which can measure much faster than this. But the problem is that basically you need to measure a certain signal, and the signal needs to be strong enough to not to suffer from noise. So this is now the most and the biggest, the highest, the biggest problem in our case. And okay, and we carried out a big set of simulations where we showed that the delay line jitter can be a problem, but unless you keep the jitter below the length of the bandwidth limited pulse length, it provides you with a reasonable reconstruction. So it can be used. Although of course the better delay line, the smaller jitter, the better for you. And by this, let me acknowledge various funding sources for which allows us to carry out the research. And I'm sorry, and let me thank you for your attention.